Welcome to tutorial 20, where we're going to be using what we learnt in tutorial 19 on D-types to now build a 1-bit counter, then a 2-bit counter, then a 4-bit counter using those D-types. Now in this activity we're going to need a little bit of extra circuitry because we are going to be providing a clock pulse into the D-type to enable the count to take place. And if you remember in the previous tutorial, the clock requires a low to high transition, i.e. a rising edge to make the D-type work. And when that appears at the clock input, whatever is on D goes to Q. Now you will notice in this circuit that once again we're employing a bit of feedback, because in this case we are feeding back, not Q, back to the input D. D is going to inform, i.e. change how Q appears when the clock changes, and whatever is on Q, the opposite will be on not Q, and that will then get fed back to D again. Now this is really what flip and flopping is all about. But first of all, let's look at this input circuit. Now there's a lot of extra components here just to press a switch. So when this switch goes low, i.e. we press it, the input to the 555 goes low and the output to the 555 goes high. So when we press the switch, the clock is going to go high. So it goes from low to high when we press the switch. Why have we got all this here? Well, by way of a simple explanation, because we are counting, we don't want pulses to bounce. Because this is a mechanical switch and these are metal contacts inside, when we press the switch it will bounce. So a little demonstration here might be, if this was the switch and I press the switch, it does that. But actually if we looked at it under a microscope it would be doing this. So you've got 3 or 4 little pulses happening, and we don't want that in our counter because we only want one pulse to happen at a time. So let's check that this little bit of circuitry works. So there's my switch, these are the extra components. My output of a 555 is pin 3. At the moment there's nothing there, so I need to turn on the power. The 555 is low, I press the switch, it goes high. I press the switch, it goes high. You can see the little pulse happening. Okay. So, looking at our circuit diagram once again, we have pin 3, pin 5, Q is pin 1, not Q is pin 2, reset is pin 4, set is pin 6. Set and reset are just held down to ground now. They need to be connected, you can't just leave them floating in the circuit. And then we are going to our LED from Q. So when I press this switch, this will go low to high. Whatever is on D will then transfer to Q. Okay, so what happens? Let me just put in the link from my input circuit to pin 3, which is the clock of the D-type. I press the switch. I press the switch. I press the switch. I press the switch. 0, 1, 0, 1. Oh. 0, 1, 0, 1. So our output of our 1-bit counter goes 0, 1, 0, 1, 0, 1. Let's build the 2-bit counter. In activity 2 we're going to be building a 2-bit counter. So here is our original counter from the first circuit. If we have another quick look at that again. So here is our original counter, 1-bit counter, and here is our input circuit. So now, without drawing out the whole circuit again, the output of our input circuit is going to come into our clock, which we already have, and now we're going to feed the output of the first counter into the input clock of the second counter. Now, a couple of things here. First of all, you will see that the output we are using from the first counter is not our Q output, which is our indicator, goes to our LED, but it is our not Q output. In other words, the opposite output of Q. And that is being fed back to the clock of the second counter. Second thing is, you will notice that I've changed the output now from just being Q, although it's labeled Q on our RDs, and I'm calling it A and I'm calling it B. And I'll explain that in a bit more detail later. So once again, we need to label the pins on here. So we already have pin 5, pin 3, pin 1, pin 2, pin 4 and pin 6. Now we're going to be using our second D-type. So we're going to need to use 9, 11, 13, 12, 10 and 8. If we have a quick look at that, those are the pins that we are using, the other D-type inside our 4013. So we'll be using these pins along here. So we press the switch, it creates a 1-bit counter that feeds out, so it feeds out into our 2-bit counter. So here we go. I press the switch, 1, and you'll notice that I've labelled them A and B. Notice that even though it's labelled A and B here, because we're drawing it this way, I'm actually putting them with A on the right, and you may recognise this from our logic that we did where we always had A on the right and B on the left. So press it again, press it again, press it again. So let's start at 0, 0. So we're at 0, 0, press the switch once, A comes on and B is still off, press it again, B is on, A is off, press it again, they are both on. Press it again, they're both off. Again, A comes on, press it again, B comes on, A goes off, press it again, they're both on. Should recognise a pattern here, pattern in many different ways. 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1 or 0 1 0 1 0 1 0 1 0 0 1 1 0 0 1 1. That is our 2-bit counter. First introduction to binary. If we give A value of 1 because this is our first column, and we give B the value of 2 because this is our second column, we have no 1s and no 2s, so that would equal 0. Here we have 1 1 plus no 2s, so that will equal 1. Here we have no 1s plus 1 2, which is 2, so that equals 2. Here we have 1 1 plus 1 2, which equals 3, and then of course we go back to 0 1 2 3. So this is counting 0 1 2 3 0 1 2 3, but it's doing that in binary. Let's move on to activity 3. So in activity 3, we're going to build a 4-bit counter. So previously we built a 1-bit counter, then we built a 2-bit counter, so we added the second bit of the D-type onto it. So the original 1-bit, we have our clock pulse coming in. We then fed not Q out into the clock pulse of the 2-bit counter. So if we now want to use a 4-bit counter, we are going to have to use another 2 D-types, and we're going to have to put them onto the side. And we're going to feed out the not Q from the second counter into the third counter, and then the output of the third counter into the fourth counter. So what I have here, there's my 1-bit counter, and then I added on a 2-bit counter. So now I'm going to add on a 3-bit counter and then a 4-bit counter. These two are from the first 4013, and these two are now going to be from the second 4013. The pin numbers, which we've already done for the 1 and 2-bit counter, are exactly the same for the 3 and the 4-bit counter. So this is just another 2-bit counter bolted onto our original 2-bit counter. However, as our clock pulse is feeding in here, this was our output A, this was our output B. Now we're going to have C and D. So looking at my circuit, you'll notice that I have labelled the outputs. Previously I had the outputs A and B, but now I've added on my other 2-bit counter with my second D type. Therefore we have C and we have D. The reason that we count in this direction rather than as it is on the sheet there from left to right A, B, C, D is because when we count least significant bit, i.e. the smallest value, to the biggest value. Originally this is worth 1, B is worth 2. So now, because it's in binary, this is worth 4 and this is worth 8. So let's do our count. So I'm going to press the switch once. A comes on. So we started with 0, 0, 0, 0, and we've now got 0, 0, 0, 1. Press it again. B comes on and A goes off. Next, A and B are on. I'm going to fill in the rest in a moment. C now comes on, so I have 1, 0, 0. Next, A comes on, 1, 0, 1. Next, 1, 1, 0. Next, 1, 1, 1. Next, all of them go off and D comes on, 1, 0, 0, 0. 1, 0, 0, 1. Next, 1, 0, 1, 0. 1, 0, 1, 1. 1, 1, 0, 0. 1, 1, 0, 1. 1, 1, 1, 0. 1, 1, 1, 1. Press it again, and it goes to 0, 0, 0, 0. So what we've done, we've gone back to here. Just fill in these. So as I've already explained, A is worth 1, B is worth 2, C is worth 4, and D is worth 8. Just like we would count in base 10, our counting method, 1, tens, hundreds, thousands. So therefore, we have no 1s plus no 2s plus no 4s plus no 8s. That equals 0. Here we have 1, 1 and nothing of anything else equals a 1. Here we have 1, 2 equals 2. Here we have 1, 1 plus 1, 2 must equal 3, same as before in our 2-bit counter. But now we work into the third column, i.e. the value 4, or C. So therefore we have 1C, which is worth 4. 1C plus 1A equals 5. 1C plus 1B, 4 plus 2 equals 6. And I'm sure you can see the pattern running all the way through 7, 8, 9, 10, 11, 12, 13, 14, and let's have a look at the last one. We have 1 8 plus 1 4 plus 1 2 plus 1 1 equals 15. That is the maximum number you can get out of a 4-bit binary number. So remember, this was originally a 1-bit counter. Then it became a 2-bit counter. Then it became a 4-bit counter. So this is a 4-bit counter. Maximum count of 15, or 1 1 1 1. So as we look at that at slightly more speed, we go 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 and 0. Now keep hold of this 4-bit counter, because it's going to be very useful after we've done the next practical.